Welcome to the ARSET training, Building Climate Risk Assessments from Local Vulnerability and Exposure. My name is Sean McCartney, and I'm an ARSET trainer based at NASA's Goddard Space Flight Center in Greenbelt, Maryland. It's a pleasure to welcome you all to the first part of this two-part webinar series. For those unfamiliar with the Applied Remote Sensing Training Program, or ARSET, ARSET is part of NASA's Applied Sciences Capacity Building Program. ARSET provides accessible, relevant, and cost-free training on remote sensing satellites, sensors, methods, tools, and applications tailored to audiences with a variety of experience levels. Our trainings cover a range of datasets and analysis tools and their applications to agriculture, climate and resilience, disasters, ecological conservation, health and air quality, and water resources. Trainings are offered online and in person, freely available to anyone with an internet connection, and conducted either live and instructor-led or asynchronous and self-paced. ARSET trainings have both bilingual and multilingual options and use only open source software and data. Since 2009, the program has reached over 100,000 participants from 170 countries. We encourage you to visit our website to learn more about the program. All ARSET materials are freely available to use and adapt for your curriculum. If you use the methods and data presented in ARSET trainings, please acknowledge the NASA Applied Remote Sensing Training Program. The following slides will provide you with an overview of the two-part webinar series. So, why is climate risk assessment important? For one, climate change impacts and risks are becoming increasingly complex and more difficult to manage. Climate change impacts on infrastructure also vary by region. And by identifying at-risk assets and the types of climate conditions that drive problematic responses, stakeholders and scientists can co-develop risk information to suitably address those risks. By following the approaches described in this two-part training, participants will be able to recognize the dramatic contextual nature of climate risk assessments and adaptation planning, identify components of their own system that are vulnerable or exposed to climate risks, work with stakeholders to construct climate risk information that is useful for their decision-making processes, and use risk information to identify adaptation strategies for implementation. The prerequisites for the two-part training are Fundamentals of Remote Sensing, Introduction to NASA Resources for Climate Change Applications, and Selecting Climate Change Projection Sets for Mitigation, Adaptation, and Risk Management Applications. Links to each of these trainings are provided, and we encourage you to go through them to familiarize yourselves with content related to this training. The two-part webinar series Introduction to NASA Resources for Climate Change Applications provides an introduction to NASA observational and modeling capabilities for the climate system, fundamentals of climate change assessment methods, and background on key terms and assumptions describing scenarios, climate impact sectors, adaptation, decision support. The two-part webinar series, Selecting Climate Change Projection Sets for Mitigation, Adaptation, and Risk Management Applications, allows one to make sense of the huge number of available climate data and modeling products, identify critical climate information needs for a given application, and track uncertainties related to selecting a subset of datasets, models, scenarios, variables, and time periods, all the way through decision support. Over these 2 days, there will be two 1.5-hour sessions which will include presentations and question and answer sessions. All materials and recordings from each session are available on the training webpage. Part 1 is focused on the theoretical framework for demand-driven climate adaptation support. There will be one homework assignment which will be posted on September 21st with a due date of October 5th. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment before the given due date. The objectives for the first part of the webinar series are as follows. By the end of part 1, participants will be able to summarize the theory of demand-driven climate adaptation support, list resources for adaptation support, and recognize demonstrative examples of impact assessment based on empirical approaches and analysis of infrastructure. Please put your questions in the questions box and we will address them at the end of the webinar. Feel free to enter your questions as we go. We will try to address all questions during the question and answer session after the webinar. The remainder of the questions will be answered in the question and answer document, which will be posted to the training website about 1 week after the training. It is now my pleasure to introduce the guest trainers for today's webinar, Dr. Alex Ruane and Sanketa Kadam. Alex is a research physical scientist at the NASA Goddard Institute for Space Studies, where he is a co-director of the GISS Climate Impacts Group and an adjunct associate research scientist at the Columbia University Center for Climate Systems Research in New York City. Alex serves as the research coordinator and climate team leader for the Agricultural Model Intercomparison and Improvement Project, an international transdisciplinary project connecting climate science, crop modeling, and economic modeling to place regional agricultural impacts of climate change into their global economic context to assess uncertainties, vulnerability, and world food security both today and in the future. Alex served as a coordinating lead author for the Intergovernmental Panel on Climate Change 6th Assessment Report, Working Group 1, Chapter 12, Climate Information for Regional Impact and for Risk Assessment. Alex's research uses a variety of climate and impacts assessment models to examine the influence of climate variability and change on a variety of sectors, including agriculture, water resources, urban areas, infrastructure, energy, and human health, leading to the development of adaptation strategies and decision support tools for stakeholders and policymakers who need to understand vulnerabilities and uncertainties to successfully manage risk. Sanketa is a PhD student in the Department of Earth and Environmental Sciences at Columbia University in New York City. She's also part of the research staff at NASA Goddard Institute for Space Studies with the Climate Impacts Group. We are delighted to have them joining us as guest trainers to discuss the theoretical framework for demand-driven climate adaptation support. Alex, over to you.
Thanks, Sean, and hi, everybody. My name is Alex Ruane, and it's my pleasure to be here helping to present this ARSET training. I'm joined by Sanketa Kadam, who is also with me at NASA Goddard Institute for Space Studies in New York City. We are going to be presenting the first part of this two-part training. Today, we will talk about the theoretical framework for demand-driven climate adaptation support. Throughout this presentation, both parts 1 and part 2, we will be presenting the material as organized along 4 different threads of information. We'll represent these with little symbols in the upper right of the slides. Where you see a green T, these are slides related to the first thread, which is the basic approach and climate risk theory that we will be using to inform adaptation planning. The purple R is a second thread related to resources and tools from NASA and partnering projects and agencies and groups that provides information that we can use for this assessment. The third thread will be represented by an orange D. These are demonstrative examples that illustrate how the theory has been applied in previous projects. You'll notice probably that we do a lot of these demonstrations using agricultural projects and urban impact projects in New York City. These are places where the NASA GISS Climate Impacts Group has a lot of work. So even though those two topics might be somewhat overrepresented, we feel that these demonstrations will allow all of you to understand the approaches and hopefully transfer the way we've done it into your own projects. The fourth thread will be represented by the blue C, and these are end-to-end examples from the Climate Adaptation Science Investigators Phase 2 initiative, also known as CASI-2. And CASI is an initiative that is informing NASA centers' efforts to increase resilience and adapt to climate risks. So rather than lots of scattered demonstrations, the idea behind this blue C, which will be the focus of the second part of this project, is to really understand the way that the whole theory comes together in one project. And for more on CASI, I'm going to turn now to my colleague, Sanketa Kadam.
Thanks, Alex. NASA utilizes its various scientific programs and research activities to support enhanced climate adaptation capabilities throughout the agency. With this specific Climate Adaptation Science Investigators Initiative, or CASI, this program spans nearly the entire USA, covering 14 of the centers and facilities shown here on the map. CASI is now in its second iteration, tackling the very important question, what are the climate threats to NASA facilities, and how can we prepare for future challenges in order to build resilience within the entire agency? CASI is motivated by experiences of climate impacts on NASA facilities and the threat of growing climate risks. Many of our NASA facilities have already experienced climate and weather-related impacts in the recent years. For example, here on the top right, you can see the impact of the 2012 Hurricane Sandy inundation to the Wallops Flight Facility, which hosts a launch site. On the bottom is the Michoud facility damaged after Hurricane Zeta in 2020. And the image on the left shows wildfires and smoke near JPL in 2009. So CASI's mission is to provide latest scientific research on climate change to help NASA managers adapt to increasing climate risks. We achieve this by collaborating with NASA scientists that are subject matter experts and managers from all the centers. These identified groups of people work together to help CASI create and provide a portfolio of key current and future climate risk information for center managers, protecting operations, assets, and workforce in and around their centers. By combining scientists and operation managers, we really co-generate products linked to decision making.
All right, so the approach that we are going to be presenting today is a way of understanding climate risk and assessing climate risk in a targeted way. To do this, we have adapted a climate risk management approach developed by colleagues in Germany. And the basic idea is presented in this circle diagram. So fundamentally, we're trying to understand climate risk. And to do that, the first step is to identify the various systems of interest and the stakeholders who are our target audience for this type of information, who are actually making decisions around climate adaptation and various planning. The second part is to develop a context-specific analysis so that rather than speaking in generic terms, we are bringing the information and the scientific approach to the level of the centers and to the level of the decisions in progress. We then evaluate risks, breaking down components of hazard, exposure, and vulnerability across different specific assets that are at risk at each center. Then we assess the magnitude and frequency of impacts and the growing or changing risks for each of these assets. And then we move into a phase where we implement and monitor in terms of identifying the specific interventions that might be motivated by the assessment. And then we have to figure out how to scale those types of interventions and contextualize them in the broader decision scope. And then monitor those actions and the changing climate risk over time to make sure that we continue to operate in a safe space. The first part of this climate risk assessment methodology is the identify phase, which we will describe a little bit more in detail now. So within this identify phase, the main goal is to identify the stakeholders by their roles and also as individual people. And what we mean by that is we want to understand their interest, their influence, and their competing constraints in whatever organization they are, but also to connect with them as people. It's not just nameless individuals that are making decisions on climate change. They have their own personalities, their own motivations. So we want to connect with these people in the positions that they have, and also connect with potentially overlapping efforts. Again, being humble and recognizing that climate risk information and climate planning is not only being done by the deliberate effort that we might have in focus today, whether it's the CASI project or a new project that you might design tomorrow. It is likely one of several competing interests and competing motivations for these stakeholders. When we are identifying, we are also trying to identify the sector problem to address and the system scale at which that problem must be addressed. And then we also want to understand the time horizons of decisions so that we can understand the timeline by which decisions are made, implemented, and evaluated for success or failure. One example of a complex system is taken here as an illustration of the food system. And we show this to illustrate that different stakeholders have unique points of leverage. So here, again, looking at the food system is much more than just an agricultural crop sitting in a field. We might think of that as the biological system, and it's affected by the weather. But of course, foods is harvested and moved beyond the farm gate into an economic system where it might be processed and traded. That is driven by demand from a social system. It might be influencing and influenced by a political system. And in the end, the point of the food system in many ways is to achieve a healthy community. So we have the health system here as well. So this is a way of representing the fact that the system of interest that you're looking at, whether it's agriculture or urban areas or water resources or health, is likely part of a much larger system. And the stakeholder has to understand where your information fits into that larger picture. And in that sense, this might look confusing, it might look complex, but you also might recognize that there are many stakeholders all along these pathways that could help the food system become more resilient. So part of what we're trying to identify is, are the stakeholders you're talking to the correct ones, or ones that can actually make a difference with the information that you provide? So understanding that system, trying to map some of this out is a very important part of this identify phase. Another thing that's important to recognize in identifying stakeholders is the time and temporal scales that their decisions affect. Stakeholder decisions have unique horizons. In this case, again, looking at the food system, you'll recognize that farmers are often concerned about what is happening today and what might be happening in the remaining weeks of this fall season, but also have an interest in the coming months and maybe what's coming next year. In the longer distance, they might be interested about the legacy of their farms, the long-term sustainability, and maybe passing on their farmland and farm operations to their children and grandchildren. But the time horizons of that farmer are uniquely distinct from the time horizons, for example, of a crop breeder who might be developing a new crop variety over the course of 1 to 10 years. When you think about the time for genetics and breeding, if you're building a reservoir, your time horizon might be a 3-year work plan, but you're hoping that reservoir will last 100 years. And as you go through this food system, you'll recognize that different people have different operations scales. And what you need to do is match the climate information to the people who are actually making decisions related to the scales of the climate information, both in time and in space. And this is important also as we're thinking about adaptation at NASA centers and for other sectors. The developed phase of our climate risk assessment methodology is again focused on how we can contextualize the analysis that we will do over the course of this assessment. The focus is to achieve context-specific analysis because it is more likely to be successful and more appealing to stakeholders, to increase buy-in and make it more likely that stakeholders will be able to use that information. This is not a scientific result, but I have found in many of our climate impacts group applications that the same risk assessment approach that is successful in one place is rarely able to be transferred to another place more than about 70% in terms of the decisions that you have to make around climate information and data sets and assumptions and methods. It's not realistic in most cases that you can absolutely transplant one scientific approach to a new context. Many of the decisions might be consistent, but you need to work with the stakeholders to round that 70% up to a 100% useful activity. And that means you have to engage around the contextual differences from one project to the next every single time. Another very important part of the develop phase of the project is to agree on a process for sustained engagement between the scientists and the stakeholders. This is to make sure that the project is run smoothly, that the information is generated and shared in a way that allows inputs from all and increases the likelihood of useful uptake. It also increases buy-in from stakeholders when they know that they have been involved and listened to throughout the project. So some of the main phases or main tasks within this develop phase is to develop and manage a communications plan, both between the project leadership and the scientists involved, as well as the stakeholders involved. And in particular, we need to develop a familiarity between the people themselves and a two-way capacity for collaboration. So one of the biggest challenges in this develop phase is to make sure that no one group is dictating all of the terms of the engagement to the others. And many times scientists have to be humble in terms of understanding the true needs of the stakeholders in this part. One example, just to illustrate again these different decision domains and hazards within New York City. Here are two illustrations of the city. On the left, you'll see the 5 boroughs of New York City with Manhattan, this island in the middle here, for those who know it. And what you'll see here is all of the sewer overflow locations where you have water treatment and different parts of runoff that can affect the surrounding environment. You'll also see in gray the wastewater treatment plants that are affecting the water coming out of different pipes. And these are important pieces of infrastructure that help New York City operate. You'll notice that these locations are predominantly along the coastline and therefore are not evenly spread out throughout this whole area. And we'll talk later about what that means for their exposure to different types of coastal risks. But the stakeholders in New York City who are responsible for these water treatment plants and sewers are quite different than the stakeholders who are responsible for the subway systems that run through New York. Here we've zoomed in on southern Manhattan and the bridges and tunnels that connect to Brooklyn. The stakeholders in charge of the subway tunnels are actually, in many cases, led by the New York State officials that oversee the Metropolitan Transit Authority in New York City. They are, of course, concerned with underground tunnels and the potential of flooding and other hazards reaching the underground tunnels and subway stations. And you could imagine that the context by which we engage these stakeholders would be different, and the types of climate information that we will discuss with each of them are also quite different. Of course, it's not just one city. We also recognize that different parts of the world have very different contexts. Here is an example taken from our Urban Climate Change Research Network, which is a community of cities around the world facing common challenges for climate change and sharing best practices across all of these different cities. Of course, within UCERN and within other contexts, you'll see that cities have different sizes, structures, both physically and politically, and different climates and different leadership. The people themselves are different. And you can imagine that whether we're talking a highly developed city or a low-income, developing, transitioning economy city, large cities, small cities, all of these things are going to be different contexts. And of course, the climate background creates a different set of risks for each of them. So again, what we're trying to emphasize here is the importance of understanding your context and how much you can transfer best practices from one to the next. One of the things that we do within several of our projects here, an example from the Agricultural Model Intercomparison and Improvement Project, or AGMIP. This is an approach that we use to engage stakeholders who are interested in climate adaptation for agricultural systems all around the world. And you'll see on the right some examples from engagement between scientists and stakeholders in India, in Zimbabwe, and in Senegal. And in each of these places, we took on a similar approach that was a process that began with thinking about the climate change risks and engaging stakeholders around risks that they have already experienced, impacts that they have already experienced, that motivate a conversation around the future of climate risk. With that group, we co-designed pathways to understand what agricultural systems might look like in the future. We develop adaptation packages that are not just one, but several different adaptation options that could be linked together to have even bigger impact than any one would be individually. And then we evaluate the projected impact of those adaptations on a future that has changed from today, both in terms of the systems and the climate risk. We look at the risks and benefit, and we link back to the beginning of this process with the stakeholders to run through this in an iterative process, every time engaging the stakeholders around how we better understand the risk, and then refining the adaptation packages so that we can get to true information that informs policies and decisions. This is just an example. We're going to go more into detail around how we've been doing it more recently, but the key emphasis here is the engagement of stakeholders throughout this process and the need for iterative and sustained stakeholder engagement. As we get to the evaluate phase of this climate risk assessment methodology, it's important to think about the different components of risk. So we want to understand the interactions between hazards that come from the climate community or from the climate system. We'll talk more about climatic impact drivers in the next slide, but these are the various climate change factors that lead to climate hazard. We also know that risk comes when there are things that are vulnerable to those climate conditions and exposed in a place where they will be where they will experience those climate conditions. And of course, we also recognize that there is the potential for responses or even our own climate adaptations and various interventions to create or modify risk in their own right. So what we need to think about as we're evaluating our context, as we're thinking about how we will assess risk in these places, is each of these components in individual and also in combination. So we have to ask questions about whether we need additional sectoral elaboration or an impact model, like a crop model or a hydrology model, maybe to augment the specific risks that we want to explore. We also need to determine the climate information needs and select the climate projection sets so that we can draw from the most important climate change factors and understand the hazards that are kicking off all of this climate risk. And then as we're thinking about interventions, we need to think about the interventions specifically in the way that they reduce the hazard, the vulnerability, or the exposure, and recognize that there is a potential for additional response risk that we would like to avoid. So let's talk more about this climatic impact driver. This is a new approach that was developed as part of an intergovernmental panel on climate change chapter that I helped lead in the last 6th assessment report cycle. For those who don't know, the Intergovernmental Panel on Climate Change, or IPCC, is a major international effort to assess the state of climate change literature and provide information for policymakers around the world. But this approach was utilized within a climate information chapter to better articulate the need to orient our climate information around the specific needs of stakeholders so that they can make decisions. And in that sense, we defined this climatic impact driver as a climate condition that directly affects elements of society or ecosystems that we care about. Climatic impact drivers and their changes in themselves are not good or bad. They can lead to positive, negative, or inconsequential outcomes, or a mixture. It's when you connect them into the system's vulnerability and exposure that they can become hazards if they cause damages, or they can become boons if they actually improve the situation. And of course, we follow this pathway. We know that there's a huge number of things in the climate system that we might be observing or tracking, but there's a smaller set of these climatic impact drivers or these climate change factors that directly lead to hazards and therefore influence risk. And we also want to track the potential for improvements or beneficial effects that come from climatic impact drivers that serve as boons and lead to longer benefits. So understanding how the climate phenomena connects into the system that you care about allows us to move from generic scientific physical terms that the climate system and climate scientists might use into more applied terms like hazards and into more functional systems like risk that stakeholders can use to make decisions. Within our IPCC chapter, we defined a set of categories of these climatic impact drivers that forms a fairly comprehensive set of climate change factors that you may want to look at in examining risks to your systems. The top line here represents major types of climatic impact drivers, including heat and cold climatic impact drivers. Sometimes we call these CIDs. The heat and cold CIDs are responsive to temperature, includes things like the average mean surface temperature, as well as more episodic extreme events like extreme heat. We have wet and dry CIDs, we have wind and storms, snow and ice and cryosphere, other categories like air chemistry and radiation, coastal CIDs and open ocean CIDs. So this becomes a set that we hope will guide some of your assessments and make sure that the assessments are not too narrowly focused on the most obvious of extreme events or climate changes that might be in the popular understanding or already on the radar screen of the stakeholders that you're talking to. So socializing, thinking about these other climate hazards and the climatic impact drivers that can lead to those hazards is an important topic of conversation as you're beginning this assessment. You'll see also that we can use this as a map in terms of the types of climate information that we might be able to categorize and organize our assessments around. One thing that we did within the IPCC is we broke each of these CID categories down in terms of how they affected different systems that we care about. So here is a segment of a much larger table that you can find in this IPCC Working Group 1, Chapter 12. And what we've done is we've broken down the food system here, and you can look at the crop systems, the row crops that you might find in a farmer's field, livestock and pasture systems, agroforestry systems, and fisheries and aquaculture systems. And you'll see that each of these has a different profile in terms of the climatic impact drivers that light up as being of high relevance, or at least low and moderate relevance to those systems. So crop systems are some of the most climate sensitive that you'll find, responding to all kinds of heat and cold events, as well as a huge number of water cycle related wet and dry climatic impact drivers, storms, a little bit around the margins of snow and ice, and in coastal agricultural zones. But as you'd imagine, crop systems are not really affected by open ocean climatic impact drivers, while those CIDs have a dramatic effect on fisheries and aquaculture systems. So by doing this type of mapping, you can actually understand the profile of climate hazards that affects each type of system that you might be interested in. And this becomes an orientation and a roadmap for the types of climate information that you're going to pursue and assess in your stakeholder engagement and overall risk assessment. Another thing that we encourage in thinking about this climatic impact driver approach is to translate responses into context-specific hazard metrics that are linked with vulnerability. So as we're making this mapping of a climatic impact driver from a physical climate condition into a risk-relevant set of information, we want to identify the specific tipping points, operational ranges, and other engineered or biophysical limits related to any given type of climate change factor. So here's an example looking at increasing daily maximum temperature and thinking of it in the context of a corn or maize plant. And the basic idea that is represented in a lot of crop growth models is that there is an optimal temperature by which a crop might grow. And then it might reach a critical temperature threshold above which growth begins to reduce because the temperature is affecting crop growth in some detrimental way. When you get to an even higher temperature, we start to talk about a limiting threshold beyond which the crop can fail quite rapidly. So understanding not just that extreme temperature might be bad for plants, but understanding that there are these biophysical connections around specific temperatures that relate to the tolerance of a plant is very important to thinking about adaptations and asking questions like, could we come up with a new seed variety that would actually raise this temperature threshold and expand the temperatures in which optimum growth can occur and thus prepare us for a warmer future. So these are the types of questions we would hope would be discussed and asked around each type of system, so that we can understand not just which climate factors, but what are the thresholds that we need to be particularly attuned for, so that we can provide climate information and understand potential nonlinear threats that could emerge in the future. Another thing that's important to discuss is the way we think about climatic impact drivers is not just about how extreme can they get in terms of their intensity. So if we're thinking about something like a heat wave, probably the first thing that comes to mind is how hot did it get? And this is related to the intensity and the magnitude of something like a heat wave. But that's not the only way that we gotta think about extremes, and it's not the only way that extremes affect the systems that we care about. So here I'm gonna set up a set of examples, just theoretical, kind of hypothetical examples. And in each case, we're gonna be comparing a current climate in blue with a future climate represented by orange or red lines. And in each of these cases, we're going to be comparing it against some hazard threshold, like that limiting crop temperature, for example. But what we have to understand is that this extreme heat or some other similar CID can be affecting the system through its intensity or magnitude, with climate change leading to higher temperatures, let's say. But it can also affect that system by increasing the frequency by which that hazard threshold is exceeded. So again, if we think about this same time series here, in a current climate, this hazard is exceeded 3 times over this time period. So you might think of it as there being 3 heat waves, whereas in the future climate, there are 5 heat waves. So this frequency can also lead to impacts that might be concerning. You might also look at the duration by which some kind of hazard event occurs. So in this case, the current climate hazard lasts a shorter period than the future climate hazard is projected to occur. And the duration might be the tipping point for some system. It's important also to look at the timing of a hazard. If it's happening earlier in the season, that could have a dramatic effect on biophysical phenology or other things that are on a schedule that we care about. You might also look at timing in relation to the speed at which a hazard becomes a problem. So in this case, you might consider something like a drought, and the speed at which you go from normal conditions and drop into a deep drought condition. In this case, in the future, it happens much more rapidly than it does in the current climate, and that can be a problem. The other thing, of course, to think about is the spatial extent of a hazard. So in this case, we might be looking at a flood map for this dark blue river and realize that in the future, the floodwaters may reach beyond the historical blue floodplains into new orange floodplains on some return period that we care about. So the challenge here is to determine the context-specific response thresholds, the suitability balance, and the operational ranges for the systems that we care about in relation to all of these ways that climate change may be affecting the specific hazards that we care about. For more on information resources that we might use to understand these geohazards, let me turn to Sanketa again.
Thanks, Alex. NASA has a broad range of information resources for geohazards, and we encourage you to learn more about these from other ARSET trainings that have been posted. But here we broadly categorize these into two types. First are the remote sensing resources like MODIS, iMerge, Landsat, satellite data to look at observational variables. Second, on the right there, NASA has excellent model and projection tools openly available for weather, climate, and coastal hazards. These are some of NASA tools that we looked into when initiating CASI work, including tools for fire risk, sea level and coastal floods, energy management for buildings, and solar energy, and forecast tools for extreme weather. Selecting a climate projection set should be based on local responses and evaluated needs, given a risk application context. So here we again call your attention to the ARSET training Alex led last year called Selecting Climate Change Projection Sets for Mitigation, Adaptation, and Risk Management Applications, where we dive deeper into finding climate information suitable for your application. Generally, the key characteristics to look at in a data set is global climate models, or what type of models you're looking at, scenarios and storylines. Downscaling, is it dynamically downscaled or statistically downscaled? Temporal resolution, spatial resolution, post-processing of the data set, if it's bias adjusted, and then applications ready variables needed to evaluate local risk. An important note here is that more complex projection sets are not necessarily better, even if they feature higher resolution. So here is a vulnerability example of data set available for New York City. And here we show the asthma hospitalizations for all ages, and you can see a spatial pattern throughout the city compared to the per capita income in the city that was recorded. And again, you see similar spatial patterns for both. Another vulnerability in exposure geoinformation resource for you is through CDAG, ASTED EM, NYC Open Data, and just another example of vulnerability and exposure resources available.
One thing that's very useful in evaluating the types of risks and hazards that are important is to create tables or maps that connect specific climate factors to specific assets that are at risk. Here's an example of wet hazards and their pathways to impact in New York City. So you can see on the left here, these are factors related to precipitation, intense precipitation like heavy rainfall, and drought conditions. And we've categorized that as part of this New York City panel on climate change. We looked at how this related to communication infrastructure in the left column and the energy infrastructure in the right column. And I won't go through each of the details, but this type of storyline that helps you understand the direct pathway by which these impacts, these climate conditions lead to impacts really helps you understand the type of information that needs to be provided and the type of responses that might be applicable. We can also take that same risk diagram, sometimes these risk diagrams are called propeller diagrams, and we can add more detail around specific assets that are at risk. So here is an example looking at risks to infrastructure that looks at the drivers within each component of risk, each determinant of risk, and how they interact within each other, and how they interact together in the broader risk framework. And we'll show in the second part some more examples of how we've done similar elaborations in our project. But this type of mapping gets to the second level and beyond, and is very helpful as an exercise with stakeholders. The other thing to note, of course, is these components of risk are affected by our actions. So the fundamental idea behind mitigation of climate change, so these are things like reducing your greenhouse gases or ecosystem destruction, those are really designed to reduce the overall level of hazard. So if we can keep the global warming levels low, if we can reduce the overall amount of climate change, then we, in many cases, can reduce the number of climate extremes and other large climatic impact drivers that we might be worried about. Adaptation is not really the same thing. Adaptation can't change the hazard itself, but it can change your vulnerability and your exposure. So it might make you more tolerant to that hazard when it happens, or it might put you in a position where that same extreme doesn't get to you in the next time. So you can change both your vulnerability and exposure. The issue, of course, also that we have to recognize in an actual application where decisions are being made is that both adaptation and mitigation may lead to response risk. Sometimes this can be called maladaptation, where you might have a benefit for one element of adaptation that leads to side effects that can be detrimental to other aspects of your system. And same thing can happen with mitigation. You might solve one problem and create another. So this is part of this contextual evaluation that we have to do as we're considering different types of interventions. We have to think about those interventions also in the context that may influence those things outside of our immediate perspective. The next phase of the climate risk assessment methodology is the assess phase, where we actually do the scientific assessment. And in particular, we're going to be focusing on the magnitude and frequency of impacts. So here is where we actually do the calculations and we make our projections around how hazards are changing. We look at all of those components of change, the magnitude or the intensity, the frequency, the duration, the timing, the spatial extent. We look at trends in the vulnerability and exposure. So it's not only the hazard that might change as we're thinking about future conditions. And then we want to evaluate the risks both with and without adaptations and proposed interventions so that we can see those in context and see if our system or if an adapted system is better positioned. And then, of course, we also want to understand that benefit. Sometimes we are not just trying to figure out if something is better or worse, but we're trying to figure out if it is cost effective and if the benefit outweighs the costs. So we need to see what we can do to quantify or understand that more completely. One way that we assess useful climate risk information comes from a World Wildlife Fund assessment project that we did in Myanmar. The Climate Impacts Group and Columbia University worked with the WWF to talk to stakeholders in that region about the types of climate events that were of concern. And one thing that we heard was the need to better understand extreme heat conditions in April, which is a very hot month in their monsoon-oriented climate. In the historical period from 1981 to 2010, the event that happened about once a month, so the hottest day of the month on average was about 39.3 degrees Celsius. As we looked to the future, we asked how that hot day would become more frequent under both a low emission scenario and a high emission scenario in the near term and in the longer term. In the near term, we projected with this 21 GCM ensemble that hottest day of the year, instead of happening just once a month, would happen on average 3 times a month in the low emissions future, and would happen 6 times. So a 6-fold increase in the hottest day of the month, the frequency of the hottest day of the month in this near-term climate under the high emissions future. When we go to the mid-century, under the low emission scenario, that hottest day of the month is occurring 4 times, and under the high emissions scenario, it is happening 17 times each month, which is more than on average once every other day. So what used to be an extreme hot condition is now happening almost every other day in that high emissions future. So the idea behind this is to show how we work with stakeholders to identify both the climatic impact driver of interest, which was heat extremes, the threshold of interest, which is a relatable hottest day of the month. And then we developed this pictogram or infographic which shows it in a very easily accessible way. And it's important that we not only create good science, but we communicate it in a way that our stakeholders can understand. And this type of approach can be applied in many other types of applications. Another thing that we are doing right now is understanding the actual impacts using additional elaborated models. So here is an example of projects in Ghana in West Africa. And we have applied a maize yield model or a corn model to understand how future climate is going to affect crop yields. And these are preliminary results, but what we wanted to show here is both the need to look at how climate and crop systems are responding across the country, but then to take those results, the crop yield results, and turn them into productivity and even economic returns for farmers, and how they change in the future if we are in a situation where there is no climate change compared to a situation where there is climate change, and even compared to an additional situation where we have implemented an adaptation package featuring heat-tolerant seed varieties. So this gives us a really nice picture to tell the stakeholders about which parts of the country are vulnerable and what will happen as climate changes if they don't act, and what might happen if they do better prepare their society. And of course, we can follow this pathway not just from the hazard to the crop yields, not just from the crop yields to the economics, but also into the policy realm where we think about larger poverty rates in that region. In this case, the adaptation package can lower the poverty rates substantially. And then we also can look at how food security can change if we can implement such an adaptation package. So these types of questions become much more operationally relevant for stakeholders who are planning their rural development policies and adaptation plans. We also can look at assessments, for example, here in New York City. These are assessed flood regions on different levels of sea level rise associated with climate change projections. And you can see the parts of New York City that are flooded under different types of conditions. In particular, we'll call your attention to the greens, yellows, and reds. These are places that don't currently flood that would flood more and more as the sea level goes up. This green area over here includes the John F. Kennedy Airport. So this is critical infrastructure that could be at risk as climate change moves up the global ocean levels. This type of information is something that really fits the interests of stakeholders in these regions who are trying to understand which assets, which people, which infrastructure, and other concerns would be affected by these types of scenarios, and therefore what types of policies or infrastructure might we put in place to harden this coastal region. The final phase of our risk assessment approach is the implement and monitor phase. And here is where we're really thinking about what those interventions might be, the scales by which we might be able to act, and how we can monitor those interventions as they are put into place and as the climate changes to see how well they're doing. So what we want to do is we want to identify the affected scales and systems, and then connect the risks that we did in our assess phase to the specific decision processes of our stakeholders so that they can compare their options given available resources. That helps them to prioritize interventions and also to define or at least articulate what they perceive to be an acceptable level of risk. That is part of the cost equation. Then we also have to think about what it takes to implement adaptations and the stated design criteria. So what are the costs? What are the proposed protection levels? What is the lifespan of equipment? All of this is important information as we think about how we will monitor the performance, as the design criteria also define, what is viewed as success or failure, and whether we are able to achieve our goals in those adaptations. The other thing that's very important to note is that we want to reassess this process continuously, because we know from our climate science that there is a non-stationary climate right now. We have a climate system that is still warming, and until we stabilize the greenhouse gas levels, we will continue to see changes. So given that there is a non-stationary climate, and given that our systems are not static and are constantly developing and changing all around us, we have to recognize the need to reassess the shifting levels of acceptable risks in this whole process. So implementing and monitoring in practice requires that adaptations have a specific hazard that they are targeting. And what I mean by that is we can't have a generic adaptation. It has to specifically reduce some vulnerability to some hazard, or reduce exposure to some particular hazard. An example of this would be something like building seawalls. Higher seawalls are designed to protect against coastal flooding, but would not alleviate extreme heat conditions. So if we're talking about an intervention and we can't articulate the hazard that we are targeting, it might not be a climate adaptation. Likewise, if we adapt to one climate hazard, it does not mean that we have solved the other climate risks. This is one of the reasons we encourage a climatic impact driver and multi-hazard approach, is we don't want to solve one climate problem and convince ourselves that we are no longer at risk for climate. We have to recognize that broader scope. This is another reason to think about adaptation packages rather than individual adaptations on their own. Thinking about how different specific adaptations linked together allows us to create synergies and co-benefits between the adaptations, mitigation options, and other center priorities or other system priorities that we might be looking at. So this is the goal, is to think about our interventions in context and responding to the combination of climate hazards that might be affecting the system that we care about. Here's just some examples of different things that were done, different implementations and actions that were done within New York City and proposed adaptations around this area. As we did assessments in New York City, we identified damaging potential of extreme heavy rainfall events. So one thing that was suggested there would be to improve the capacity for rapid collection of heavy rainfall. That basically means allowing our sewers and pumps to retain stormwater in holding areas and to move it through the system more rapidly. That also includes natural landscape and drainage and plans for controlled flooding. We also looked at storm surge and water treatment and raised the elevation of key infrastructure along coastal areas, including some of those water treatment pumps. We also had watertight containment of key equipment around some subway areas and some energy systems, and also increased the number of reserves of key equipment to prepare for flooding events. We also installed local protective barriers and also recognized that there are some places that inundation is not cost effective to prevent, but if we could define those areas and plan on inundation in the way that we control those areas, that could have a benefit. So these are the types of examples of how climate information might be brought into larger sets of planning and implemented in ways that improve the resilience of a region. As we were doing this in New York with this New York City panel on climate change, we recognized again the importance of flexible adaptation pathways. And here I'll just show one kind of theoretical picture where if we think of the x-axis here as being time and the y-axis as risk, there is a status quo if we think of a climate change situation where risk is increasing, that over time we will have a line like this, the risk goes up. If we have some kind of an adaptation, we can lower that risk. We can prevent, especially on the short term, we might be able to lower the risk. But as the climate continues to change or as the adaptation begins to degrade, that risk may start to rise again. So this is an example or illustrates the risk of an inflexible adaptation approach where we solve the problem once and then walk away. What makes a lot more sense is to recognize that the level of acceptable risk can actually go up and down over time, depending on socioeconomic change and policy, and even the people who are in positions of decision making. If we recognize that there is an acceptable level of risk that might not itself be a static quantity, then we can continue to monitor and reassess the system over time and build adaptation pathways that are able to recognize when we get close to that level of risk, or maybe even exceed it slightly, and respond in ways that allow us to reduce risk over time. And this allows us to stay in a situation where we remain underneath this acceptable level of risk and stay on top of non-stationary systems and climate. So I think with that, we are at the end of our first part. Just as a summary and a status check as to where we are. As part of part one, we have introduced this theoretical approach for demand-driven climate adaptation support, rooted in 5 phases of climate risk assessment. These were the identify, develop, evaluate, assess, and then the implement and monitor phase. Each of these have key tasks and ways that we engage with the stakeholder community and with the scientific resources and scientific experts. But it is also designed in this circular manner because it has to be a reassessed and continuously monitored system that allows us, as we iterate through the system and as we actually make implementations, to stay on top of the science and the stakeholder context as it changes through time. The result of this process is contextual adaptation support, motivated by stakeholder interests, built upon local data and expertise, utilizing a right scale climate information set, connecting adaptations to specific risks, and linked to decision structures and contexts. In 2 days, we will present part 2 of this ARSET training, which will elaborate on the theoretical approach that we presented here and show how it is practiced by this Climate Adaptation Science Investigators Initiative, or CASI, that is informing NASA climate adaptation efforts. And our hope in that end-to-end demonstration example with CASI is to show how all of these pieces can come together and the way that stakeholders and scientists can work together for a more useful set of climate risk information. Thank you very much.
Alex and Sanketa, thank you both for the terrific presentation. As a reminder, there will be one homework assignment which you can access on the training page starting on September 21st. Answers must be submitted by Google Form with a due date of October 5th. A certificate of completion will be awarded to those who attend all live webinars and complete the homework assignment by the deadline. You will receive a certificate via email approximately 2 months after completion of the course. Below is the contact information for Dr. Alex Ruane and Sanketa Kadam, along with links to the training webpage, website, and social media. If you enjoyed today's webinar, we hope you will sign up on the ARSET listserv to receive notifications for future trainings, and follow us on Twitter or X for other relevant announcements pertaining to NASA's Earth Sciences. We will now transition to the question and answer portion of today's webinar. Thank you. Wonderful, and I want to thank everybody that's been contributing their questions. We've gotten some really, really good ones. So again, if you do have a question, it's not too late. Do submit it in the question box. So just jumping right into it, question 1. For slide 27, are all these farming inputs included in the assessment, or do you include the input that connects more to the identified question?
What we do within AgMIP is we develop models along the different scales and systems within this broader farming system. So we have detailed farm system models that are based on the weather and the soils and the genetics, as well as the farmer management. And there we apply models by crop species. So we have wheat models and maize models and soybean models. We also have household models that look at the net returns for a farm household that might feature multiple fields, livestock, equipment, and costs for supplies and labor, but there is kind of an overall net economic returns focus. And then, of course, we take what happens on all of these farms and link them together into regional and global models of production so that we can assess things like land use and trade and prices. Here, seeing much more influence from government policies and the socioeconomic demand. So by building up elements of each of these components of the food system and then linking them together, we can resolve more interactions and learn more about the current and future risks. Certainly, we're not covering every single possible thing, but we are trying to capture the main crux of the challenge.
Great, thank you, Alex. Question 2, concerning the step of development, agree on the process. It will not be possible to manage this cooperation between stakeholders and scientists using a different approach or model, such as the quadruple helix model. This approach also allows for the inclusion of citizens, a group that is typically excluded from the decision-making process and the creation of solutions, often only being involved in the consultation phase.
So yeah, Alex again here. I've seen this happen, certainly, that some projects and some activities will have a wide variety of people involved in early consultation phases, but it's important that they're involved with representative stakeholders in the early phases, in the iterative phases, and in the final assessment phases of the project, especially related to kind of decision making. These are it's difficult to do because stakeholders have their own competing interests and time pressures. But finding some stakeholders that can represent these broader groups is very, very important. And in particular, you have to fall out of the trap of only speaking to the administrators or the agency representatives, policymakers, or powerful private sector interests. So I'll acknowledge that this is a lingering challenge, but this is why we wanted to emphasize it here, because it's really important that you go out and find groups that can represent that. And we've been successful in projects like AgMIP at bringing in farmers and others that are outside of the traditional conversation. It's also important to recognize people who are related. So for example, we try to make sure that there's gender balance and considerations involving younger and older people as well. Multiple perspectives is very, very important for buy-in and the likelihood of lasting successes.
Great. Question number 3, what drivers are important or needed to be considered while working in inland cities?
So inland cities are unique in the sense that they don't have the coastal or open ocean risks, but of course, all of those other climatic impact drivers may be relevant. So oftentimes there will be extreme temperatures or shifts in the water cycle or storms or cryosphere ice type hazards that are under consideration. In most cases, when you speak with stakeholders, they are keenly aware of at least a few prominent vulnerabilities. So you might talk to somebody in Eastern Oregon and they are very aware of the risk of fire, or somebody in parts of the South that are very worried about extreme heat events. So the challenge and the important thing is to ask questions about all of the climatic impact drivers, because there may be others that are smaller but still influential, and it may be possible to alleviate those risks more easily. It's also possible that some of those smaller risks may emerge as larger hazards in the future. Or those climatic impact drivers will emerge as substantial climate hazards in the future. So the risk profile may change over time. So in both coastal and inland cities, go through all of the CIDs, but of course in the inland cities, you likely can cross off the coastal risks.
Great. Question number 4, would context-specific hazard metrics be equivalent to damage functions?
So damage functions are related, but I would draw some distinguishing characteristics here. Damage functions are often built upon context-specific hazard indices, but may imply a direct relationship from that hazard to the impact given, or to the impact given the information on vulnerability. So I don't want to speak too broadly. Some damage functions are quite complex. Some are quite simplified or based on empirical relationships. But in some cases, what we do is we employ some kind of detailed sectoral model, like a crop model, to understand the implications of future change. And these may actually involve multiple hazard metrics and information about multiple types of intersecting, compounding, or sequential type hazards. So they're not exactly the same, but of course very related.
Great. Question 5. The humanitarian approach these days, with the help of technology, is shifting its focus from response to preparedness, and anticipatory actions are saving lives and properties. Can you please share your thoughts on how technology can contribute to this? How about incorporating anticipatory action in the risk triangle too, so as to minimize it?
So we are very much our climate impacts group has a mission to effectively provide climate risk information to allow people to take both reactive but also proactive actions. The proactive side is really, really important because many of the adaptations that we want to do take time to develop and implement. It's not always ready when the hazard strikes. So some examples of that is based on our scientific reports. In New York City, Mayor Bloomberg raised the elevation of the water treatment plant pumps in anticipation of future sea level rise and coastal flooding. In agriculture, we work with breeding companies that have told us that their research and development cycle, if they're trying to build new varieties that have heat or flood or drought tolerance, those can take 10 years or more. To not just do the genetics and the breeding, but to then mass produce and get the seeds out there. So the idea behind these proactive and anticipatory actions, in some cases you have to implement before the hazard strikes, and in some cases you're trying to create interventions that will be ready down the road when you need them. It's also important to note that it's not just technology, but you can be proactive with policies and subsidies and market development so that we can build up resilience and have more good options for the future.
Great. Question 6. I am searching for real-time temperature data from satellites. Where can I find such data? I'll go ahead and answer this one through the LANCE. That is a project that NASA is sponsoring out of Marshall Space Flight Center. You can get MODIS data, that's moderate resolution imaging spectral radiometer data, and that's available within 60 to 125 minutes, so 1 hour to 2 hours after a satellite overpass. And this is near real time, so it's not real time, but it's pretty close. It's near real time, and you can get that again through the LANCE, and this is including land surface temperature, but also some other derived level 3 and 4 products that they're giving. And so we've provided a link to this, and we've also will state that in other previous ARSET trainings, we've also explained some of the methods and tools to be able to access and use this near real time data. So moving on to question 7, around when can we see the SWOT mission data in the NASA worldview? I'll go ahead and answer this one as well. We're unaware of the timeline, so we cannot state any given date, but hopefully they will be able to get that hopefully this year. It's a relatively recent mission that launched, and so I think the logistics of getting that onto the worldview have been made somewhat cumbersome, but hopefully they'll have that up later this year. Question 8, how are vulnerability and exposure maps created, and what were the data used?
So I'll answer this one here. There are lots of examples for exposure. This is something that is traditional kind of mapping. So you can find GIS data sets that map out the infrastructure, residences, farms, ecosystems, and other assets that you might care about. Depends where you are, depends on investments locally in terms of data collection. And also sometimes these maps are not updated as frequently as you would like. But you can find these types of maps through GIS databases that are organized by public, private, and academic institutions. So an example from NASA is we have the CDAC, and in New York City you can find GIS maps of lots of different things. Vulnerability information, I would say, is much more difficult to map out, particularly because there's a lot of types of vulnerability to explore. So we have used our impact models to stress test systems, like our crop models, to stress test different crop systems. That means we effectively run our models with increasingly warm conditions, let's say, which allows us to identify the response to heat. And we've done similar things for drought and carbon dioxide impacts. From that, we can reveal strong regional and system-dependent vulnerability patterns that may inform this process. But of course, true on-the-ground measurement is the best thing to do. It's just very difficult because the systems are changing very rapidly. So this, I would say, is probably the most data sparse component of the risk propeller at present.
Great. Question number 9. When will NASA CDAC be currently updated?
I'm not exactly sure on this question, but NASA CDAC has a devoted staff that is constantly looking for new data sets and updates to existing data sets. So this is the answer is kind of every day, but there are certain things maybe around scenarios and some of those areas that fall under the IPCC cycle. And CDAC is also collating data sets that come from external locations, kind of like what we said above. So looking at public and private and academic databases.
Great, thanks, Alex. Question 10, are there data on location/density concentrated animal feeding operations?
So this is another one I don't have any resources really to point you towards off the top of my head. I'd imagine that USDA has some of this information. And the locations, I think probably the follow-up question would be, what can you tell me about these locations? So animals, number of heads of animals, and what type of operation it is. I'm not personally familiar with that type of information, but maybe people know of some that they could put into the chat, and I would look to the USDA as a starting point on that.
Great, thank you. Question number 11. I've always understood vulnerability as defined by exposure, sensitivity, and response/adaptive capacity. Why is vulnerability, exposure, and response being treated separately in this case?
Thanks. Yeah, if I guess, Brock, if you could scroll down so I can keep track of what I've already thought a little bit about for question 11 here. Yeah, so this is the approach that we have presented here is one that was adopted within the IPCC. In the Google Doc, I have a link to that, and we'll make sure that we get that out. It's pretty easy to search for. Actually, I helped develop that document. So if you look up IPCC guidance document on risk and my name, Ruane, it should come up pretty fast on an internet search. But it really wasn't just me. What we were doing there was assessing the literature and looking at a large amount of approaches that have been taken. And we wanted to apply a similar methodology across all phases of the IPCC. And this one was quite attractive. I think it works quite well in distinguishing different components of risk, but also maintaining their ties to the specific hazards. And this goes to some of the information I was sharing about how, risk alleviation can't be done in general. It has to be targeted towards specific hazards and vulnerable things that are exposed. So we, the breakdown that the questioner asked included something like sensitivity. I think that's pretty close to what we mean by vulnerability. Adaptive capacity is a little bit different because it's almost like the time change, or the ability to change your vulnerability over time. So that's a slightly different dimension. And of course, risk can change over time. And one way to reduce risk is to reduce your vulnerability. So that is something that we can track, but it fits well with this methodology. And I don't remember what the third component was, not being able to see the question. Sean, could you just read for me one more time on question 11? It was sensitivity, adaptive.
Yes, absolutely. Yes, there was okay, I'm sorry. Why is vulnerability, exposure, and response being treated separately in this case?
Yeah, but in the second sentence, I think it was something about different components that they had treated, sensitivity.
I've always understood vulnerability as defined by exposure, sensitivity, and response/adaptive capacity.
All right, so I think I did address it. So the exposure is what we call exposure, the sensitivity is what we call vulnerability, and then adaptive capacity, you might think of as your ability to change that vulnerability, or maybe even your exposure over time. So I think the approach that we've taken by splitting into these three propellers and acknowledging that those propellers can change over time, we're covering the same ground, just with a slightly different way.
Great, thank you, Alex. How do you assess, question 12, how do you assess the risk without adaptation? Isn't it extremely complicated to set up a counterfactual as adaptation efforts are overly location specific?
So the risk, there's a couple of different ways we can do this. So we can look at impacts in the past. And in this sense, the counterfactual would be, what if we had adapted in the past? That's a specific set of historical counterfactual information that you could consider. Going into the future, we often set up two different types of scenarios, with and without adaptation. And we really, for the most part, many systems, especially writ large, the idea of zero adaptation is not very plausible, because people will at least take autonomous or easily readily available type adaptation options, as the conditions change. And in some cases, if we can be proactive, there may be more transformational. And in some cases, even without proactive, the conditions themselves will force some kind of more dramatic adaptation. But the reason to show both with and without adaptations is when you show without adaptation, it may motivate the idea that things have to change. So, once you can solve that first question with stakeholders, that the status quo may not be viable out into the future, or maybe there are conditions where it is, that's the first conversation. But then the second question is, okay, under which adaptations do we see risk changing, and by about how much? This becomes a way that you can start to prioritize different adaptation strategies and identify new ones. So the answer is not to only do one, the answer is to do both with or without and with several different types of adaptations, ideally getting to adaptation packages that have been iteratively developed through this process with the stakeholders and the scientists working together.
Great, thanks so much, Alex. Say question number 13, a quick question on the section and WWF Myanmar example. This was done in 2017. How frequently would we expect to go back and see if our forecasted hazards and impacts have occurred? For example, 5 years later or 10 years or more?
It's a good question. So this Myanmar example was actually looking out towards the middle of the century. So we're not really yet in a position to go back and see if these hazards have occurred. But of course, between 2017 and today, you can look to see if there have been the type of extreme heat events moving in the type of direction that we have seen in our projections, for later in this century. There's kind of a couple things that would motivate a going back to see what's happening. One of them would be if there is new science that has changed the overall set of projections. So this could be a new set of CMIP climate model runs. That's the Coupled Model Comparison Project. So if there are new climate model projections, has the situation changed? Another one that you might look at is if the system itself has changed in some kind of dramatic way that would change your overall set of vulnerability or exposure, you may want to reassess risk for that. So the short answer is, if there is reason that the risk has changed or the risk assessment would have changed through any of those propellers, then that might be reason to go back and look. And of course, every single time a new paper is published might not motivate an entire new risk assessment process, because these can cost money and resources and time and attention. So that is something that has to be balanced against the resource availability. And certainly you also have to be cognizant of stakeholder fatigue. And in that sense, it's probably best to use benchmarking kind of efforts that meet the scientific and system changes that are most prominent.
Great. Question 14, how accurate are the global climate models when it comes to a city level assessment? As per my understanding, the course of resolution makes it difficult to perform the analysis at a granular level. What can be the possible workarounds to help the stakeholders interested in taking actions at a higher spatial scale? Any references would be great.
All right, so this is one of the topics that we're going to get into more in part 2 of this training. And I would also refer you back to the ARSET training that we did last year around selecting climate projection sets, which had an entire section on kind of the importance of spatial resolution as a distinguishing factor. And Sanketa mentioned this in her part of today's presentation. But we will talk about in part 2 how we use a bias adjusted and downscaled version of some climate model outputs. But maybe what I'll use this as an opportunity to say is that some CIDs, some climatic impact drivers, are more or less scalable than others. So if we're looking at something like the mean temperature change, there is certainly small scale patterns of mean temperature differences. So for example, in New York City, Central Park is a little bit cooler than the surrounding, highly concrete and apartment building parts of the city. That pattern probably won't change, but if the mean temperature is rising by a degree or two in all places, or if it's rising by, let's say, 2 degrees in New York City, you would likely see something close to that 2-degree increase in each of those places, even as those local mean temperature patterns persist. And some other patterns like that are more persistent than others. Around severe storms, around certain types of extreme heat or air quality, you can get secondary features that come into play, especially around complex terrain and high kind of mountains, coastlines, mountains, things like that. So this is definitely a factor, and I'd encourage you to look at that ARSET training and part 2 of this for some more details about how we do that.
Great, thank you, Alex. Question number 15, can any country apply for mitigation package or evaluation?
I'm not exactly sure what this question is. I mean, NASA is not performing these for just anybody who asks, but certainly the scientific approach that we've laid out here is one that could be applied for a large number of countries and a large number of their most important assets. So this is something that would need to be adapted, and we would encourage, and one of the purposes of this training is to increase the overall capacity of all of you to perform this type of assessment. There are groups out there, there are projects out there that have indicated interest in helping countries with this type of activity in terms of making scientific tools available. The work we do with AgMIP, for example, is very interested in collaborating with countries and their local scientific experts to understand the future of agricultural risk. But that's probably the best I can say for now.
Okay, and question 16, to what extent is this methodology appropriate to use in combination with intersectional vulnerability analyses, and how would we integrate the two?
So this is getting at the question, or it's getting at a key feature of why we call these climatic impact drivers. You'll notice in the term climatic impact drivers, and I'm gonna watch as people take notes in the section here, climatic impact drivers has a hyphen between impact and driver. And the reason for that is because what we're looking at here are lots of impact drivers for every system. We know that there's social change, there's technological change, cultural changes. All of these things can cause impacts on your future system. But what we are focusing on for this situation is the climatic impact drivers. So this is something that we are especially looking at, how changes in the climate system are driving impact on the things that we care about. And these changes and the shifts in risk that we are assessing here absolutely have to be connected to other changes and other pressures on these systems. And this is why you heard us use the word, or use the phrase being humble several times in this presentation, is that we know that the stakeholders are weighing multiple competing and at times, overlapping and sometimes synergizing, but sometimes competing pressures in terms of the decisions that they're making. And the climate information, climate risk shifts are part of that equation, but not the entirety of it. So that kind of intersectional approach where we look at climate changes in the context of other changes is very important.
Wonderful. Well, looking at the time, we are at the 12:30 Eastern time. So this is the end stop time for this part 1 of the webinar series. For those actually, thank you for everybody that did submit a question. We understand that we did not get to all of them, but we will be going back through and answering all the questions that were submitted, and we will have this uploaded to the training page by next week. So do go to the training page. And as we wrap up, I do want to thank Dr. Alex Ruane and Nick Palacio, as well as Sanketa Kadam, for giving such a wonderful presentation and everything. And Alex, I wanted to know, as we wrap up, if you had any last closing thoughts or comments for all the participants on today's webinar.
My only, well, first of all, thank you all for listening and asking some very interesting questions. We are excited to share part 2 and feel that this overall presentation is really completed by seeing both parts. Some of the things that we really wanted to show in part 1, we moved to part 2 for the overall rounding of the two. So hopefully if this has been interesting, watch part 2 to see the rest. And if what you wanted wasn't quite what you saw here, it might be in part 2 as we're trying to turn the theory and the data sets into specific applications seen end to end. So thanks again. And as we've said several times, these types of collaborations are ongoing. So if you have specific interests, please feel free to reach out and we can see what is possible.
Great. And as Alex just alluded to, the second part, again, will be in 2 days at the same time. So we hope that you would join us for the second and final part of this webinar series. And again, a very big thanks, Dr. Alex Ruane, Nick Palacio, and Sanketa Kadam. Thank you for presenting and providing the wonderful materials. I also want to thank the entire ARSET team. That's Amita Mekta, Brock Blevins, Jonathan O'Brien, Sarah Cutshall, and Sue Monthie. So thank you for everybody on behalf of ARSET. We look forward to seeing you in 2 days for part 2 of this webinar series. Thank you.